All right, let's talk here about a few topics, various topics in number theory. We started talking about number theory last time. So this is just a few more topics in number theory. It's just some terminology and then some other ideas, I guess we might call it. One thing, a lot of times in number theory, they notice there is patterns and things, because we're just talking about the natural numbers, the counting numbers in number theory. Well, one thing to notice. There's a thing called twin primes, and this kind of gets back to something we talked about earlier. If you go through the prime numbers, 2, 3, 5, 7, 9, 9's not prime, 11, 13, 17, 19, you just see a lot of these primes grouped together like that are different by just two numbers. And we kind of explored that a little bit last time. But anyway, they do give a name to that phenomenon, and that is twin primes. Twin primes are just simply primes that differ by 2. And there's going to be a few of them out there, right? And just on the few I've written up here, we've got those. 5 and 7 are twin primes. 11 and 13 are twin primes. 17 and 19. Even 3 and 5, we could put those on there. But there's just a lot of those. We said last time we looked at that list, that chart. Remember the chart that had 2 through 7, and then 8, 9, and then they were one more, one less than a multiple of 6. We talked about all that last time. So just because of that fact, there's a lot of them out there. Twin primes is what they call it. There's also another type of prime. Let me tell you about here. And these are Mersenne Primes. Mersenne being a French name, last name, but anyway, Mersenne primes, they are primes that can be written in the form two to the n minus 1. In other words, these are primes that, it's a power of 2 minus 1. Power of 2 minus 1. Turns out there's a few of those as well. Some of these are Mersenne. Not all primes are Mersenne primes, but there are quite a few of them. For example, well, let's just do 3. 3 actually is going to be the smallest prime that would fit into this category, because do you see there that there's a power of 2 minus 1 that gives you 3? What power of 2 that if you subtract 1 from it would give you 3? 2 to the 2, right? 2 to the second minus 1. 2 to the second is 4, and then minus 1 you get 3, don't you? Okay, so 3 we say is a Mersenne prime. You might think, well, that's kind of strange that they would come up with that, but that's that is what it is. Now, one other thing let me mention before I talk about this some more, but does that remind you of anything? That little formula? Well, you remember the number of subsets was 2 to the nth power, right? And then minus 1 was the number of proper subsets. So interestingly enough, this formula is the same as that. And then also, well, we didn't mention it much, but there's a lot of things that are 2 to a power. In this case, it's 2 to the power minus 1. But anyway, now that's the smallest Mersenne prime. What would be the next one, you think? Well, try the next power of 2, right? 2 to another power minus 1, 2 to the third power minus 1. What does that give you? 2 to the third is 8. Then minus 1 is 7. So 7 is also a Mersenne prime. Now notice, this is the first Mersenne prime, this is the second Mersenne prime. So there are some prime numbers that are not going to fit into this category, right? Like 2 is not a Mersenne prime, 5 is not a Mersenne prime. So there's only some of them that are Mersenne primes. So anyway, now here's another thing. What's the next Mersenne prime? Well, you might be thinking, what about 2 to the 4th? But there's a little problem with 2 to the 4th minus 1. 2 to the 4th minus 1, 2 to the 4th is 16. 2 times 2 times 2 times 2 gives you 16. And then minus 1 gives you 15. What's wrong with that? 15 prime? No. It's not a Mersenne prime because, of course, it has to be prime to be a Mersenne prime. They sometimes call it Mersenne number, but we're just interested right now focusing on the Mersenne primes. So 15 is not. The next one, actually go 2 to the 5th minus 1. 2 to the 5th is 32, and then minus 1 is 31, and it is on the prime number list, so there's another Mersenne prime. And let's go ahead and try 2 to the 6th minus 1. 2 to the 6th would be 64, and then minus 1 is 63. So again, is 63 prime? No. So again, we're out of the prime realm there. So even you have to be careful on your powers. Now, what you might note there is what kind of power is giving us this prime number. Aren't the powers prime themselves? 2 to the 2nd is prime. The 2 is prime. The 3 is prime. The 5 is prime. 4 is not prime. 4 is not prime. So yeah, it turns out for it to even possibly be a prime number here, that power has to be a prime number 2. 2 to the 7th would be the next one. But anyway, the power has to be prime number itself, yeah. But anyway, that's Mersenne prime, and I'm going to say more about that here in a moment. But for now, let's move on to another topic, and we'll come back to these in just a second. All right. We just mentioned the idea of subsets and proper subsets. Well, there's a little term in number theory that's similar to proper subsets in set theory, and that would be proper factors or proper divisors. Probably most often it's referred to as a proper divisor, but it's proper factors as well. Okay, remember what a proper subset was. A proper subset was a subset that was what? Proper subsets. You know, you have your subsets, and then you have a proper subset. A proper what else did it have to be? Smaller, right? It had to be a smaller set. For the subset to be a proper subset, it had to be a smaller. Well, it's the very same idea on proper divisors. If I want to list only the proper divisors of, say, 12. To be a proper divisor, it has to be a divisor that's less than the number itself. Okay? So the proper divisors of 12, 1 is a divisor of 12. And of course, by divisor, I mean factor as well. 1's a factor divisor. 2, what else? 3, 4, and 6. Now, 12 is a factor, 12 is a divisor, but it's not a proper divisor because, again, with proper divisors, we're only talking smaller numbers that are divisors. Okay? So 1, 2, 3, 4, and 6 are the proper divisors of 12. So just leave off, basically you leave off just one number, right? So that's proper divisors. Now, the reason I mention that is because these next three things I want to talk about here have to do with the proper divisors. First of all, it's a perfect number. Yeah, there does exist perfect numbers. There's not any perfect people, but there are perfect numbers, okay? And here's how, in number theory, they define that. Perfect number is going to be a number that is equal to the sum of its proper divisors. A number that is equal to the sum of its proper divisors. Believe it or not, such a thing exists. Now, 12 is not a perfect number because if you add those up, what do you get? 1 plus 2 plus 3 plus 4 plus 6 gives you not 12. Okay, so it's not, that one's not a perfect one. But that's what we're going to be doing with the 16. All right. So unfortunately, that one is not. However, let's look at 6. What are the proper divisors of 6? 1, 1 and 2, and 3, 1 and 2 and 3. What do those add up to be? Aha. There's an example of a number that's equal to the sum of its proper divisors. So 6 is a perfect number. Matter of fact, it's the smallest perfect number. Okay, well, we have to go down the list a little bit to find the second one. Let's look at 28. What are the proper divisors of 28? 1, 2, what's next? 4, and then 7 and 14. What is 1 plus 2 plus 4? The sum there of those. Check this out. 1 plus 2 plus 4 plus 7 plus 14 is 28, isn't it? So there you go. There's another one that's equal to its proper divisors. So 28 is a perfect number, and it's the second, if you will, if you're talking smallest, start at the smallest. 28 is the second perfect number of the counting numbers. All right, well, I think in the homework they have you verify these, but let me just tell you the next two. The third perfect number is 496. Yep. Have to jump way up there. And I have you verify this in the homework set that I give you. And then 8128, 8,128 is the fourth one in line, perfect number. So these are few and far between, these perfect numbers. But interestingly enough, just another little factoid here for you. Do you notice this one is 6, this one is 28? Do you see a link in these two? This one ends in 6, this one ends in 28. Yeah. Turns out that all perfect numbers either end in 6 or 28. But interesting little fact. But anyway, yeah, there's a lot of ground between those. So the other two that are linked to the proper divisors are what we're going to mention next. So